Looking at the worksheet answer for the problems of 31. The first problem is about carbon-14, but it's not a radiometric dating. It's about how carbon-14 is created and decays. So we have two equations, one for how carbon-14 is created in the atmosphere. You have a nitrogen, and we say this comes from the sun. What's coming from the sun actually is protons. Protons are the primary thing that's coming from the sun, but when they hit the atmosphere, they're going to collide with things and cause nuclear reactions. They're producing the neutrons here that then are causing carbon-14. So it's kind of a chain reaction. So a neutron hits a nitrogen-14. That's your most common isotope of nitrogen-14. And so now you have one nucleon plus 14 nucleons is 15 nucleons. 0 protons plus 7 protons is 7 protons. You have nitrogen 715. Now, nitrogen 715 is a stable isotope, but not this variation. This one is unstable, and right, so you can have the nucleus in an excited state or a ground state, and this is an excited state that will break apart. And that nucleus breaks into carbon-14 and a proton. Now, let's notice the charge. There were 0 electrons, 7 electrons, still 7 electrons, still 7 electrons, which is why that has a minus sign, and 0 electrons. So this is going to have a mass of a carbon-14 plus an electron, and this will have the mass of a proton. Oftentimes when we do this for math calculations, we will say that this is equivalent to a neutral carbon-14 plus a hydrogen atom. What's the difference in the proton and the hydrogen atom? The hydrogen atom has the extra electron. So what this has done is taken that extra electron and moved it over to the hydrogen. So that's the way we usually would actually do this to account for charge, but you have to be careful that you correctly account. So we need to energy, or the equation for the energy of this reaction, which is the mass of the parents minus the mass of the daughters. I'm going to change colors. Mass of the parents minus mass of the daughters times c squared. So putting in my terms, the mass of the parents is going to be the mass of a neutron plus a mass of nitrogen 14. And then the mass of the daughters would be the mass of, and I have to choose now, what am I going to do? Am I going to do the carbon-14 plus an electron plus a proton, or carbon-14 plus a hydrogen? I'm going to go ahead and choose, because this is the way I did it, the mass of carbon-14 is the mass of its extra electron plus the mass of a proton. And then I have to multiply this by c squared. So we have to look up the mass of a neutron. The mass of a neutron is 1.008665 atomic mass units, plus the mass of a nitrogen-14, which is 14. And for some reason, I'm not showing all of my digits here. Plus 14.00307402 minus mass of carbon-14, and this is neutral carbon-14, is 14.00. Go away. Please go away. 324199 atomic mass units. I forgot to put atomic mass unit over here. I'm going to fix it now before I forget. We go on forever. Plus the mass of an electron, which is, and I recalculated this in reverse, so my digits may not be exactly right here. And when I say in reverse, I actually took the energy, the rest energy, in mega electron volts, which is why I wrote an E there by accident. It's 8. That's supposed to be an 8. And that's what I wrote down. Mass of proton. Now, like I said, I actually used the masses and calculated this from my conversion factor. So now what do? Well, let us remember that C squared is 931.494 MeV per U, right? That's C squared is equal to that. And so I'm going to write down below what I actually used for my calculation, just so. It's my hand touches the screen. Just what can you do? So using that 931.494, if I calculate through then the mass of the neutron in MeV per C squared, oddly enough, is 939.5656. So I said per C squared, but I'm multiplying by the C squared, so that's why it's just an MeV. And then the mass of the nitrogen 14 is 13,043.78. And then the mass of the carbon 14 is 13,043.94. Mass of the electron is 0.510999. And the mass of the proton is 938.2723. So that was done by distributing that C squared value through to all the numbers. And so this gives me a total number then of 0.626. Now I just truncated it to 3 significant digits. We have, from what I've written, we had 4 that I wrote there. I actually should have had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total digits. 1, 2, 3, 4, 5, 6, 7. So I dropped 2 digits there, and that just comes from reading my spreadsheet. 7794. Nice work. Okay, so we should have out to actually one more decimal place. And likewise, these had additional decimal place. 13.04 or 13,043.9359. So for correct decimal places, I should have 0.6259. So there's my disintegration energy, which now when I did this, it should have been a negative value, I do believe. I am not sure why I have. Well, that is what I have. Assuming I did all things right, then this actually doesn't have an endothermic reaction. It's an exothermic reaction. You could have a neutron coming in with very little energy, and you have enough energy to make this go because it's dropping to a lower energy state. So it's exothermic, and exo spelled with an X. exothermic because it has a positive disintegration energy or positive reaction energy, which means it's releasing energy. Now, what I was thinking when I wrote this was that it had a negative value, so the neutron would have to come in with that amount of energy. And so for my calculations, I went ahead and said that all of this energy is held by 6259 by the neutron when it collides. Obviously, it wouldn't matter. The neutron could be stationary, but I'm going to go ahead and do the work like I intended, even though I flubbed there. Now, calculate the disintegration energy for the second reaction. So the second reaction, Q is again equal to mass parent minus mass daughter. But now the parent is going to be the carbon-14, and this is a neutral carbon-14, minus, and the mass of the daughter is going to be the nitrogen, mass of nitrogen, 14, plus the mass of an electron, plus the mass of that neutrino. And as I said in the instructions, we are going, and don't forget the c squared, we are going to just ignore the mass of that neutrino. It's very small. And so this is a simpler calculation. And once again, bringing in the c squared, the mass of the carbon-14 is the same as I used up here, 13,043.9359 MeV minus, and then I have the mass of the nitrogen 14, which is the same 14.00307.402 MeV, plus the mass of an electron, which we've also done that one already, 0.000598858. Copy the wrong number. That was the mass in atomic mass units. So is that. Copied both of those wrong. Should have been mass of the nitrogen 14. 13,043.7794 MeV. And then 0.510999 MeV for the electron. And I've already multiplied by the c squared, so I don't write that again. And so doing that calculation, I have 0.1565 MeV is released in this reaction. And then I said calculate the gamma for the initial neutron, assuming that all of this energy that's released in the reaction was held by the neutron. That was, like I said, boo-boo. And calculate speed. So the first thing I did was to calculate gamma. Now we know that kinetic energy is equal to gamma minus 1 mc squared. And total energy is equal to gamma mc squared. And rest energy is equal to mc squared. So I can calculate what gamma is just by taking kinetic energy over rest energy is equal to gamma minus 1 mc squared divided by mc squared. Mc squareds cancel. Is equal to gamma minus 1. So gamma is equal to 1 plus kinetic energy over the rest energy. Yes, sir.
So I'm having problems understanding 2B and C.
I paused this incorrectly last time. We'll try again and see what happens. Okay. I really hope it's back recording. So we can calculate gamma actually very easily here. It's 1 plus kinetic energy over E0. So I've already written down the rest energies. For instance, it's 13,043.9359 for carbon-14, 13,043.7794 for nitrogen-14, Or, since we're dealing with a neutron, it is right here, 939.5656. So for the neutron, 1 plus the kinetic energy, which is 0.629 MeV, divided by 939.56. And so that's going to give me a pretty low gamma. That's a gamma of 1.000, 3 zeros, and then 3 sixes. Now, anyone who's paying attention realizes you've got too many sig figs there. You only had 4 sig figs, and now you've got 7 sig figs. Yes, that's true. I am breaking rules here with my sig figs. If we do the same thing for the electron, though, the electron, we have an energy of 0.1565, 1 plus 0.1565, and this one here, no, divided by 0.50999 MeV, 5109999 MeV, yeah. That gives us the gamma for the electron is 1.306. There, I'll use the correct number of sig figs there. So that's my gamma for the electron. Now you can look at this right away and you realize, well, the electron is going faster because that's a much bigger gamma. But we've learned since gamma is defined as 1 over the square root of 1 minus v squared over c squared, then v is equal to c times the square root of 1 minus 1 over gamma squared. And so doing that for each one of these, you find this is going 0.0365c, whereas the electron is 0.643c. So the electron is cooking at a relativistic speed, whereas the neutron, that's a non-relativistic speed, right? That's less than a tenth the speed of light. Okay, so that's the first one, and once again, I apologize for A. I was thinking it was going to be negative when I did my work. I got those numbers and didn't think about what they meant. Problem 2. While we know the concentration of carbon-14, carbon-12 changes in time, for instance, when you have a volcanic eruption, it will change dramatically. When you have a nuclear bomb, it will change dramatically. For the purposes of this problem, we're going to assume the ratios remain constant. Now remember, for radiometric dating, they actually calibrate this very carefully because they know the assumption of a constant carbon-14 is just wrong. So suppose you find a bone in your backyard and suspecting that it is an ancient dinosaur bone, you send it to a lab for testing. For grins, they run a carbon-14 test on it and find that it has some, meaning that it could not be a dinosaur bone. They find the ratio of carbon-14 to carbon-12 in the bone is 6.84 times 10 to the minus 14. How old is the bone? First question is, why is the presence of carbon-14 logically excluded from being a dinosaur bone? Dinosaurs lived in the Mesozoic, which is in the ballpark of 60 million years ago. Yes, that's just a date somewhere in the Mesozoic. I actually didn't look it up, but my recollection is 60 million is in the middle of the Mesozoic. So if we're looking at something 60 million years old, we think, but the half-life for carbon-14 is equal to 5,730 years. So if you go 5,730 years, you cut it in half. If you go, 2 half-lives, 1/4. By the time you've gone about 10 half-lives, the amount of carbon-14 you start with is so small that you have an unmeasurably small amount of carbon-14 remaining. So as a good rule of thumb, carbon-14 dating can only give you out to about 10 half-lives. Anything beyond that, you just don't have any measurable amount of carbon-14. So that's somewhere in the ballpark of 50,000 years. I'm using a round number here. So carbon-14 can only give you a reliable date out to about 50,000 years. Beyond 50,000 years, statistically, you just don't expect to find any carbon-14. Now, you notice I have this parenthetical statement that there have been numerous dinosaur bones now that have been found to have carbon-14 in them, which throws a monkey wrench in the whole thing. And, in preparing this problem, I was reading up, and, some people are like, well, they were contaminated samples. And other people are, yeah, we've done everything we can to not have contaminated samples. This part was contaminated, but the part that was sampled was not contaminated. There's a lot of contention there. But if you find carbon-14 in a pristine, preserved dinosaur bone, you really have a problem, because there should be none if it's as old as it's supposed to be. Why did people even start looking at carbon-14? Because they were suspicious, because they found, soft tissues, things that looked like soft tissues in dinosaurs, and soft tissues likewise have a lifetime. You can't preserve a soft tissue for more than a few, 10,000 years or less. And so having soft tissues in dinosaurs is what got this whole thing started. Like, maybe our dating is wrong. So we have carbon-14, we have soft tissues. It has taken away some of my belief in the radiometric dating. I still fundamentally believe it, but I'm not as confident anymore. All right. So are you done? Excellent. Doing the calculation for how old this is, we have the ratio at any time should be the ratio we started with, e to the minus lambda t, right? So if I want to solve that for time, I'll divide both sides by r0. And I have r over r0 equals e to the minus lambda t. Well, to get t by itself, I just take the natural log of both sides. Let's use purple. Natural log of that is the natural log of this, but natural log of an exponential is just the exponent. And so dividing everything by minus lambda, I have t is equal to minus natural log of r over r0 divided by lambda. Now, what is lambda? Lambda is the decay constant. So the decay constant is natural log of 2 divided by the half-life. So I'm going to actually use this and notice I have a minus natural log. Well, I can change that. I can make that a plus natural log and reverse or flip the positions. So I took the inverse of the argument of the natural log. And so now I just have to put in my numbers. So putting in my numbers, that's going to be the final is 6. Very unnice. I said I flipped it, and I didn't. There, now I flipped it. Natural log of my initial value, 1.35 times 10 to the minus 12 over natural log of my final, which is 6.84 times 10 to the 14th. Multiply that by the half-life and divide by natural log of 2. And I end up with an age of, I was looking at my own writing instead of my calculation, of 24,700 years. 24,700 years. That's, of course, well within that 50,000 year range I said we can logically use carbon 14 for. That would, by a biblical perspective, be approximately 20,000 years before the flood. For short age creationists, that doesn't work. This is just a problem. It's not meant to be something that has you delving into the age of the earth or the age of life on the earth, but just understanding how the calculations work. All right, I hope you're ready for the test. I also hope I can